Okay, what I'd like to take a look at for a few minutes today is to talk about how to look at and how to analyze graphs. And even though this whole topic has been aimed at AP Physics 1, how we look at these graphs can really be used in any AP class, AP Physics C. It doesn't matter. What I want the kids to do, I want the kids to do several things when they see a graph in the problem. I truly don't care if they read the problem at first. I want them first to look at the graph. I want them to understand, what is it a graph of? What's on the x-axis? What's on the y-axis? What exactly are we looking at? Because sometimes these graphs can look similar, and we see a position versus time and think velocity versus time or vice versa. The second thing I want them to do is to take a look at the slope. What information is the slope conveying, if anything? Sometimes the slope doesn't give us information, and that's important to recognize. The kids know slope is rise over run, which is change in y over change in x. Perfect. That's what I want them to look at. Look at the y-axis term over the x-axis term. Look at this in terms of the x and y-axis, as I just said, and look at the units. Sometimes the units will tell us what the slope of that graph means, if it means anything. The third thing I want them to look at is the area. Now, this is the area between the curve and the x-axis. X-axis. I sometimes refer to this as the area underneath the curve, which can be a little confusing when the curve is below the x-axis. So the area is simply our y-axis times delta x, our x-axis. Again, I want them to look at this in the terms of the axes, and we're going to look at an example of this in just a minute, and in terms of the units. Once they do these three things, then what is the question? And that's when I want them to start thinking about it. I want them to have an idea in their head what the graph information is conveying, so that when they read the question, it hopefully will be a little bit more clear as to how to analyze it quickly. So let me run through an example of what I was just talking about. Let's say we have a position versus time graph, and it looks something like that, nice and just a straight linear line. When they see this graph, I want them to look at, I am looking at position and time. This is where an object is, where it is located as a function of time. I just want them to think that. Then I want them to think the slope. In a position versus time graph, this is the change in x over the change in time. This is my change in y over change in x, my rise over run. In units, meters and seconds. And so what this tells me is my slope is the velocity, how fast something is going. And in actuality, that's it. This is my average velocity of this graph. And so I want them to recognize that. I want them to look at the area. Now in this case, what we're looking at for the area is height times width, basically. So that's x times time, if you want to say that. We're taking meters times seconds. And this is, I have no idea what it is. It's a meter second. That doesn't mean anything. So here's a case where the slope has meaningful information, but the area does not. So now we're looking at the slope. And what do I see about the slope? I see it's constant. And since the slope is constant and the slope is at velocity, then that tells me this object is moving with constant velocity, which means acceleration is 0. There's no net force acting on it. And so here's another curve. And then let's take a look at this. And this stuff still applies. It's still position versus time. My slope area still means the same thing. I'm looking at the slope. And what I'm seeing here with the slope is that it's a changing slope. As we go along with time, the slope is gradually getting steeper. And so, because it's a changing slope, what this tells me is my velocity is changing. And since the slope is becoming steeper and steeper, this tells me that velocity is increasing. Now, regardless of whether it's increasing or decreasing, since I have a changing slope, I have a non-zero acceleration. And so that tells me we have a net force acting on it. And then, once I have that understanding, I can I want them to read and answer the question, and that's going to tune them in a little bit better on what the problem is dealing with. So let's look at another example. That was a position versus time. Now let's look at a velocity versus time. And the reason I like doing these on particular graphs is we see them a lot. And so you have to be pretty familiar with them. So on a velocity versus time graph, and let's just do something flatlined. We're going to do it again. Same thing. I'm looking at velocity. This is how fast an object is moving as a function of time. We're going to do the same thing. This is how fast an object is moving as a function of time. Now, it's pretty clear it's moving at the same speed, but let's look at the process. Let's look at what the slope tells us. Here, and when we talk about rise over run, we're looking at change in velocity divided by change in time. Hopefully you recognize that as acceleration. The area, we're looking at velocity times time, meters per second times second. So here, this means something. We have meters. So here the area is displacement. How far does the object go in some time period? So you got to be, sometimes the slope means something, sometimes it doesn't. Sometimes the area means something, sometimes it doesn't. You just have to be careful about it. So in this particular case, when we're dealing with a zero slope, that means we don't have a change in velocity, which means acceleration is 0. Let's look at an example using the area. And let's say this, and let's just begin at time, let's say this is t naught at time is equal to 0. And I want this to be t1. And the question is, how far does it go in this time period, t1? I want to look at that area, which is simply, it looks like a rectangle. So the distance it goes is simply the height, the velocity, times our change in time, and that's how we work with the area curve. If the slope was something a little different, so let me try this marker again, and let's say our slope, we have a constant linear slope. What I'm seeing is constant slope means a constant acceleration. Our velocity is always changing. We can still get this area if we want the time from 0 to t1. That's the area of a triangle. And so we can still use these ideas. The graphs that we're going to give are not going to be real curvy, so you'll be able to figure out the slopes in the areas fairly easily. So now let's look at a series of graphs that we run into a lot. And I've already introduced 2 of them. Let's look at the position versus time graph. excuse me, let's look at the velocity versus time graph and the acceleration versus time graph. And let's just look at a couple of comparisons and some common things, because you're going to have to be able to go between these three graphs. There's more graphs, by the way, than just these few, but it's very common that if you're given a position versus time graph that is a linear line, that you're expected to be able to sketch the velocity versus time graph, which is basically you're plotting the slope of this curve. Since the slope is not changing, I have a horizontal line. For the acceleration versus time, I'm plotting the slope of this curve, which is 0, and so it's hard, you're right along the 0, right along that x-axis there, which is not unusual to get that question. So now let's look at what happens if we have a constant positive acceleration. We can't have a constant negative acceleration. That's acceleration due to gravity. And so we have a constant positive acceleration. Velocity, on the velocity graph, I should have a constant positive slope, something that looks like this. If I have a constant positive slope on my velocity graph, I have an upward slope on my x-axis, but it's constantly changing. So this is a little bit trickier. So since we have a constant slope, I get my nice linear line. But now we're constantly changing velocity, which means we have a changing slope, and our curve's going to be more quadratic, which is actually what it is. It's a quadratic curve. You need to be able to go from position versus time to velocity versus time, from velocity versus time to acceleration versus time, and then, or from acceleration to velocity versus time, and then a velocity versus a position versus time curve. So let me do a little bit of a summary with the graphs. There's a lot of other graphs that we're going to run into that I didn't talk about, but the same things apply. Look at the graph. Look at the XY axis. Look at the slope, the rise over run, change in Y over the change in X. Look at the area. This is important information. This is how we analyze these graphs. A couple of things to keep in mind. When we're looking at the slope, whether it's positive or whether it's negative, matters. That's important. A lot of time we're dealing with vectors. So we're dealing with a positive vector or a negative vector. Positive direction or a negative direction. Or we might be dealing with energy. And from Unit 3, we talked about positive work, negative work. Positive work, we're adding energy to it. Negative work, we're taking energy out. And so this information is also conveyed in the graph. Keep in mind that the slope or the area might not mean nothing. If you're not sure, look at the formula sheet. Put the y-axis variable over the x-axis variable. See if that's an equation on the formula sheet. Put the y-axis times the x-axis. See if that's an equation on the formula sheet. One of these will always mean something. There's no reason to give you a graph otherwise, quite honestly. So make sure when you're looking at the graph, either the slope or the area, one of the two, if not both, have meaning. Understand what it is. That's a quick summary on graphs. Like I said, it applies to so many things. Be very careful about graphs. I love to have graphs on my test, and I want the kids to do this. I hope this was some help. Good luck.